Right, this is going to be the second half of our overview of section 1.6, where we discuss composition of functions, where we take the outputs of one function and put them into another one. So the way to do it is, if we're given two functions, some f and g of x, f of x and g of x, we can think of x as some magic box that essentially replicates anything we put into it. So f composed with g means that we take our g and stick it into our f, and anywhere where there was an x that we had an f, we now stick the entirety of g. And if we have g composed with f, we do it the other way around. We take our outputs of f, and everywhere where there was an x we had in g, we then plug in everything we had for f. Okay. All right. So we take the output of one function and turn that into the input of the next function, or the outer function, if you will. All right, so let's take two examples. Here is a quadratic. F of x is equal to x squared plus 1. G of x is negative 2x plus 3. Okay. So if we take f of g of x, so this is going to be f composed with g. What we do is, inside of our magic box, instead of an x, we stick the entirety of g. So everywhere where there was an x, instead of x squared, we have the quantity minus 2x plus 3, and that is squared. Okay. Now when we square it out, we can treat that as minus 2x plus 3 times minus 2x plus 3. Okay. Minus 2x times minus 2x, minus times minus is a plus, 2 times 2 is 4, x times x is x squared. We're going to get a minus 2x times 3, which is a minus 6x, but we're going to get a 3 times a minus 2x, which is another minus 6x, leading us to a minus 12x. 3 times 3 is 9, and we still have our plus 1 that we had outside. So we do our addition. Well, we don't have any squares, so we're going to have a 4x squared. We don't have any x's, so we're going to have a minus 12x. And 9 plus 1 is 10. And that leads to our resulting function, this quadratic from here, right? That, has a bottom value of 1. Okay. All right. Now, g of f of x. Now in this one we take all of our f and stick that where our x was before. Okay, so we're going to have a minus 2 times this entire thing now. Okay, so f of g of x is equal to minus 2 times our quantity x squared plus 1, and then we have our plus 3 that we had left over. Okay. Well, minus 2 times x squared is minus 2x squared. Minus 2 times a positive 1 is a minus 2. And then we combine things. A minus 2x squared, well, we don't have any x squareds, so that is a minus 2x squared. Minus 2 plus 3 adds together for a 1. Okay, leading us to this quadratic, which is this thing right here. Okay. Now, clearly, this quadratic and this quadratic are not the same. So what this means is that in general, f of g is not going to be equal to g of f in general. Okay, you take the output of one thing, put it in the other. If we do it the opposite way, we don't get the same thing, right? So this is like if I buy a car for $25,000, my input is $25,000, my output is the car. If I then turn around in a month and I try to sell the car, I'm not going to get $25,000 back, right? The inverse function where I input the car and I get out money is not the same as inputting the money to get out the car. Okay? All right. Let's look at an example where we get sort of an inverse. Okay, so here we're going to have our quadratic, our classic quadratic x squared, and our classic root, square root of x. Okay. Now, square root of x only works for x greater than or equal to 0. Okay. This will have implications here. Okay. Now, first off, g, the square root itself is also defined as the positive, right? This root is only the positive piece, right? We only get pieces that are above. Our output is 0 or greater, right? G is also greater than or equal to 0. Okay? All right, so let's take our G and plug it into our F and see what we get. Okay? So when we stick G into F, we're sticking a square root of x in for x, right? Okay. So we know that the square and the square root, they kind of undo each other. But unfortunately, the square root of x only exists for x being greater than or equal to 0. So we're building it with something that only exists for positive x. So something that only exists for positive x, it doesn't matter what we do, we're never going to get anything over here. There's nothing here. Because we don't have any inputs that will work on that side. Okay? So the output, square root of x squared, well, that's just x because they undo each other, but they only undo each other in the positive half because those are the only inputs that our inside function allows. Okay? So the square root of x only works for x greater than or equal to 0, so when we plug it into something, we don't magically get those values back. What happens if we do it the other way? Okay? Now, x squared is perfectly well defined on both the positive and the negative. Okay? So we only have to worry about if the thing under the square root ever goes negative. But if we look at our function, f is always greater than or equal to 0. That means when we do our root, this always exists. It only always exists, but it's always positive. Okay? So a function that always exists and is always positive, well, the absolute value is one of them. Okay? Now, we know that the x and the square root, they undo each other. So on the positive side, this has to act just like x. Okay? But since we inputted something that's always positive, we're certainly going to get values over here. Okay? And the square root is always positive. Okay? And our x squared is an even function. So sticking an even function into something means that we have to get an even function out. So if it goes up like this over here, it has to come down like this over here. Okay? So that's why the square root of x squared is the absolute value of x. We have symmetry argument. We have an algebraic argument. Okay? So that's why the square root of x squared is the absolute value of x, whereas the square root of x squared is x, but only on the positive side because we're disallowing, half of the number line as an input. Okay, let's take a look at our next, I'm calling it a pathological example. Okay, all right, so here we're going to take a quadratic input minus x squared minus 2. This thing is less than or equal to negative 2 everywhere. Okay? We don't have any outputs that are above negative 2. Now g of x, well, it's certainly, g is going to be greater than or equal to 0 because the square root is defined as positive. But it only exists for x greater than or equal to negative 1. Okay? Okay? This is going to have implications in terms of both of our compositions. When we stick g into f, we're only going to allow x's greater than or equal to -1. And when we stick f into g, well, we're going to have to wait and see what happens there. All right. When we stick g into f, we're going to stick our entire g in for our x. Okay? The negative stays out front. Okay, that's still there. We're going to square our square root, so that's going to undo each other. And then we're still going to have our -2 that's going to hang out at the end. Okay? Well, the square and the square root, they cancel each other out. Okay? So we're going to get a minus x plus 1. We're going to distribute our negative in. So we're going to get a negative x. We're going to get a -1. -1 minus 2 is a -3. Okay? But since our input only existed for x greater than or equal to -1, our output also only exists greater than or equal to -1. Okay? We don't have anything happening to the left of that because we built it with something that doesn't exist over there. Now, when we plug f into g, okay, right, we plug it in. So instead of x, we will stick our entire negative x squared minus 2. Okay, well, we don't have any other negative x squareds. We don't have any other x squareds. -2 plus 1 is a -1. So we're taking the square root of negative x squared minus 1. Okay. Now, this thing has a maximum of -1. But the square root can't have anything less than 0 in it, right? Our inputs for our f are -2 and below, but we need at least -1 to go into our g, and we don't have that. Okay? This thing is going to be less than or equal to -1, which is less than 0, which means the square root of this thing is not going to exist. We don't have any outputs of this function at all. We're trying to input things that break our other function. Okay? So we have to be aware of that. If we allow for complex numbers, well, that's a different story, but we haven't talked about them, and we won't yet. Okay. So the magic of our compositions is we take the entire function and place it wherever our x is. We treat the x as a magic box where we stick the entire other function. Okay? Everywhere an x appears, we stick the entire other function. All right. Keep practicing. Good luck. There are several examples on the web. And I hope to see you in class.